Welcome, and let's talk about chemolithoautotrophs, aka lithotroph means an organism that can degrade inorganic chemicals for lunch. We're talking about rock eaters. And maybe you've seen the never-ending story with the rock eater. And in fact, while that's really cool, and by the way, if you haven't seen the never-ending story, that's your homework. But it doesn't happen for large multicellular organisms. In fact, it is the prokaryotic world that is responsible for utilizing inorganic chemicals as their donuts. They are capable of literally eating things like household ammonia cleaner for dinner. They're capable of degrading those things that we would look on as being poisons or toxins. So the ability to break down inorganic chemicals and utilize those as a source of energy is extremely valuable in many niches. One of those, of course, is an environment in which there is no light. If we think about primary producers in our environment where there is light, we remember that, of course, they're getting their energy from that light. But in an environment like a deep hydrothermal vent, there is no light to serve as an energy source. And so the primary producers, right, the autotrophs, those that can build organic carbon from inorganic carbon, they have to be able to live off of something inorganic, and they can't access light in those environments. So chemolithoautotrophs are the primary producers of those environments. Let's talk about some of the inorganic compounds that a chemolithoautotroph can oxidize. Imagine looking at explosive hydrogen gas as being your source of energy. You'd be like, woohoo, explosive gas, that's what I want my donuts to look like. And you'd rip and strip your high energy electrons off of hydrogen gas. Sulfur bacteria, remember the really smelly smell that you smell when you get out of the car at Yellowstone, especially at Norris Geyser Basin? That's hydrogen sulfide gas. Kind of smells like rotten eggs, at least if it's present in concentrations that won't kill you. If the smell goes away, watch out, because those are high concentrations. So imagine being a bacterium that was capable of oxidizing that smelly rotten egg hydrogen sulfide gas as your form of energy. Or maybe even iron. Oxidizing iron, making it go from the ferrous form to the ferric form. Nitrifying bacteria, they look at things like nitrite, super toxic, and utilize that as their energy source. Some utilize ammonia. We talked about the household cleaner. That's what's for dinner. But what's weird is that these oxidizers are not all that much different than we are. Remember, we're chemoorganoheterotrophs. So the kind of chemicals that we eat are our donuts. They're our organic carbons. But what chemolithoautotrophs do with their donuts is the same as what we do with ours. We rip and strip high energy electrons off of them, and we take those electrons to an ETC. We pass those electrons from one member to the next member to the next member of the ETC, pumping protons, making a PMF, tapping into that PMF to make ATP. Well, that's the exact same thing that a hydrogen bacterium does. It rips and strips high energy electrons, takes them to an ETC, and makes a PMF with them. And in fact, crazily enough, many of these unusual hydrogen-eating bacteria still use oxygen as their source of a terminal electron acceptor. So they're not all that much different with what they do with the electrons. They're just different with what they eat to get the electrons. One of the very, very famous environments in which you will find chemolithoautotrophs is in acid mine drainage. Remember talking about the acid mine drainage spill outside of Durango? Well, my hometown of Leadville is also a place where there is copious acid mine drainage. If you're out for a good time, you can head out on the bike path and look around, and you'll see acid mine drainage to the side of the bike path. This is looking out over the collegiate peaks from up at one of the high points of the bike path. And you can see that there is an awful lot of dissolved ions in this environment. So many chemolithoautotrophs get their dinner here. They're capable of oxidizing both iron and sulfur in these environments. And one of the most famous types of bacteria that lives in this acid mine drainage is something fittingly called Thiobacillus ferrooxidans. Thiobacillus ferrooxidans eats iron pyrite. You got it, fool's gold. Every good Leadvilleite has a piece of fool's gold that they keep around their house. When I was a little girl, we had one that we used as a doorstop. So iron pyrite can be oxidized by thiobacillus ferrooxidans, and it can create this very, very highly acidic environment. So you can see that in this reaction, when iron pyrite is oxidized, it forms an iron hydroxide. But look at the other product of this reaction. You'll hopefully recognize that as the super strong acid, sulfuric acid. So in these environments where there's a lot of leftover mining activity, there's a lot of acid being produced from the oxidation, the chemolithoautotrophic oxidation of rocks, right? Fool's gold. So with that in mind, I hope you go off and think more. Use your sexy mind to consider acid mine drainage and to consider what role chemolithoautotrophic bacteria are playing within these very polluted mine drainage sites.